Hello everyone, welcome to my talk today. My name is Gang Liu. I'm going to present you Zen, a high-throughput log-free OLTP engine for low-volatile memory. This is joint work with Leying Chen and Professor Shimin Chen at the Institute of Computing Technology, Chinese Academy of Sciences. Our motivation considers two aspects. From the aspect of hardware, NVM is byte-addressable, non-volatile, and large enough to store the whole OLTP database. However, NVM is modestly stored than DRAM. If considering data persistence, NVM is much slower. From the aspect of software, main memory OLTP engines are capable of processing over 1 million transactions per second in a single server. However, they use logging to support durability, which incurs I/O overhead. Hence, we would like to consider NVM and redesign an OLTP engine. The engine uses NVM as durable storage. Our goal is to achieve high throughput and fast recovery. The left figure shows the design of MMDB. It may use NVM as volatile memory. As a result, it becomes slower when the database uses more NVM to store data. More importantly, it has redundant NVM writes because it needs to write logs and checkpoints. The middle figure shows the design of write-behind logging. It keeps concurrency control-related metadata in NVM. As a result, it incurs frequent per-tuple metadata modification, and it needs tuple-level NVM space management, which incurs overhead. The right figure shows the design of feeders. It incurs read amplification by reading the whole page for a tuple. It also incurs write amplification because it transforms logs into the snapshot in NVM. We observe three challenges. The first is tuple metadata modification. In MMDB and write-behind logging, the per-tuple metadata is stored in NVM. Unfortunately, concurrency control methods may write this metadata even for read operations. The second is NVM write redundancy. In MMDB and feeders, each tuple is written to the table storage log, checkpoint, or snapshot, which incurs 2 or 3 NVM writes. The third is NVM space management. Write-behind logging manages NVM space in tuple level, which incurs significant overhead. We propose Zen to address above challenges. First, we design the table structure in both DRAM and NVM. Each table has a meta-cache in DRAM, a tuple heap in NVM, and several tuple-level space managers. Second, we place system-related metadata in NVM. Third, we keep transaction private data and indexes in DRAM. For the first challenge, we propose metadata-enhanced tuple cache to shift the tuple metadata modification from NVM to DRAM. And shown in the right of the figure, we store base table in a heap. Each tuple in the heap is identified by its tuple ID and the commit timestamp. Although the timestamp and tuple ID exist as metadata, this metadata will only be written once along with the tuple. As shown in the left of the figure, each entry of meta-cache includes concurrency control-related metadata, a pointer that points to a durable tuple, and a cache-related data structure. We use an example to show the working mechanism of meta-cache. Initially, we have committed tuple X, Y, Z, and W in NVM tuple heap. Then, a transaction comes to read X and a cache miss happens. The transaction fetches X into the meta-cache. Importantly, the transaction fails CC-meta for concurrency control. From then on, reading the tuple may change the metadata. The same happens with Y. We support all concurrency control methods. In this example, suppose we use MVCC. When the transaction writes X, The transaction creates X prime in metacache, and its CC meta points to X. Because CC meta is in DRAM, we avoid NVM writes for concurrency control, and we perform concurrency control completely in DRAM. Besides, we may adapt CC meta to support different concurrency control methods. For the second challenge, we propose log-free persistent transaction. It completely removes logs, checkpoint, or snapshot. To achieve that, we propose an atomic flag, namely LP, to mark the completion of a persistent transaction. Following above example, the transaction commits at the timestamp of 3. Then X prime is persisted with LP set to 0. Then Y prime is persisted with LP set to 1. The LP bit is persisted along with the tuple. Hence, no redundant NVM writes for each committed tuple. For the third challenge, we propose lightweight NVM space management. We divide the NVM space management into 2 levels. At the page level, we track the usage of NVM pages. Hence, we must write NVM. At the tuple level, we manage the NVM space by handling its address in DRAM. Hence, we avoid writing NVM. Upon breakdown, we collect this NVM space during recovery. Hence, we avoid NVM writes for tuple-level space management. We implemented Zen in Cicada and DBX1000. We use a machine with Intel Optane memory, and we use YCSB and TPCC as our benchmark. In this figure, the x-axis shows the workload and the different read-write ratio and the contention skill. The y-axis shows the throughput for each case. We observe 2 general trends for all designs. First, more NVM writes leads to lower throughput because write is slower than read in NVM. Second, higher scale brings 2 effects. Higher scale makes our cache work more efficiently. Hence, in read-only case, the throughput increases as the scale increases. However, higher scale also results in more conflicts. Hence, in write-heavy case, the throughput first increases and then decreases as the scale increases. Overall, Zen outperforms existing designs by 1.1 to 10.1 times under different settings. In TPCC NP benchmark, we observe that Zen is the best OLTP design. We also observe that Zen scales to 32 threads. These figures show that Zen achieves fast recovery. Using 16 threads, Zen spent less than 10 seconds for the database of a few hundred gigabytes. This figure shows that Zen supports 10 concurrency control methods, including 1 partition-based method, 3 log-based methods, 3 OCC and 3 MVCC methods. Overall, Zen achieves 1.1 to 4.6 speedup compared with the other 2 designs. For more detail about our recovery algorithm and the application of persistent indexes, please refer to our paper and code. In conclusion, NVM is promising and revolutionary for OLTP database because it's large, durable, and byte-addressable. As a result, we propose Zen, an NVM-based OLTP engine that includes 3 novel techniques. Experiments show that Zen achieves high throughput and fast recovery. Besides, Zen is flexible to support concurrency control methods. Thank you for your time.